Hello, in this presentation I will talk about the paper Orchestration between Computational Thinking and Mathematics. My name is Camilla and I'm a PhD student at Aalborg University in Denmark. Today I'm going to talk about a project I have been working on over a couple of years entitled Computational Thinking in Mathematics. Over the last few years, researchers and educators have recognized computational thinking as a strong educational approach. The basic idea is that it's more about the thought processes than about using technology. Computational thinking draws on strategies from computer science, such as organizing data, divided problems into parts, interpreting patterns and models, and designing and implementing algorithms. I will start by giving a brief overview of what I'm actually going to talk about. I will begin with an introduction of computational thinking in educational settings, and then move on to talk about socio-cultural learning perspective, and at last I will then cover some results from a developed analytical model. Computational thinking is understood in the project as the thought processes that occur when a problem is formulated and associated solutions are expressed so that a computer, human or machine, can execute them effectively. Those two definitions are similar because they're related to a cognitive and systematic process and clarified that CT can be used with and without a computer. In this perspective, CT is in the project seen as a thought processes that is independent of technology but can be used with and without technology. In the context of mathematics, I looked at how students can be supported in their thought processes and use this strategy to help them understand mathematical concepts. I believe that the core elements of CT can help students create meaning based on mathematical concept by making thinking transparent through the use of different forms of representations. Here I have a particular focus on computational thinking concerning mathematics. Based on this, it is looked at whatever computational thinking can help students understand mathematical problems through, among other things, programming, algorithm thinking, and computational representations. The theoretical framework for this project is drawing from a social cultural perspective that focuses on thought processes and peer collaboration. In the process of knowledge creation, a student's learning must be visible for the teachers so that the teacher can help each student with misunderstandings. By participating in discussion, asking questions, and using artifacts, students can truly discover content that motivates learning and gain a deeper understanding of mathematical concepts. With this in mind, students who study mathematical concepts by themselves will recognize the process of integrating CT into mathematics, CT-related symbols, and mathematical concepts. During growth, students develop spontaneous concepts as well as scientific concepts with the support of adults or more knowledgeable peers. Language plays an essential role in this mediation, where the mediation moves from an external to an internal plane through internalization. Internalization describes how an individual reconstructs an external influence into an internal understanding, which becomes a part of a higher mental function. The mediation is based on using science and artifacts and how human consciousness acts in the social and physical world. From a social cultural perspective, humans do not act in the social and physical worlds without mediations. Instead, all humans connected with the world occurs indirectly or is mediated by science. So, it is important to create interventions that focus on experience during the process of thinking and learning. So the goal is to facilitate learning through CT strategies in mathematics. So actually, learning how to learn mathematics through CT strategies. I will now dive into the developed model. The model can serve as a tool to support teachers according to working with CT in mathematics. The model can also be compared and evaluate the mediating processes that occur when CT is involved in interactions with mathematics. Analyzing based on the model will unfold the general knowledge about working with CT in mathematics teaching. The model consists of two dimensions. one of which is based on the interplay between CT and mathematics. The second dimension is established on the interplay concerning teachers and student-centered perspectives. The interplay between CT and mathematics emerged through theoretical perspectives, which are essential to how teachers mediate and construct teaching activities to support their students' development of mathematical scientific concepts. The term orchestrating relates to the teacher's function in facilitating various activities that mediate the creations of student symbol and relationship between science and scientific concept. The mediation process is concerning how subjects are using mediating artifacts to understand and cover the objects. The interaction between the teacher and student-centered activities is founded significantly. The teacher should facilitate different activities that support the student's development of CT in mathematics. Facilitating CT seems important, and so is the teacher's role to conceptualize the factual and conceptual knowledge to help students develop an understanding of a given mathematical problem. Recently, researchers have found that it is important for students to develop their own opinions and understandings regarding engagement in computation. By dealing with the connection between spontaneous and scientific concepts, students can start to recognize mathematical concepts in depth. CT highlights the meaning of students thinking about the fundamentals of mathematics, and mediation offers a connection to the social and cultural processes and personal higher mental developments. The model is represented by 4 squares. Every square is referring to diverse teaching activities that can take place during a teaching sequences. Square 1 illustrates the focus on managing activities and students' outcome. Here the teachers control the activities. In Square 2, the more traditional approach to mathematics, which incorporate a more textbook-driven approach. Here the teacher also manages those activities. In Square 3, it's a more focus on developing CT activities based on a more problem-oriented approach in which tasks are more student-centered. In Square 4, there's a more student-centered focus on task, and task is incorporating a more open approach and focusing on students' collaborations and development of mathematics scientific concepts. The 2 dimensions and the 4 squares should not be seen separately, but as a perspective that supports the mediation processes when CT is included in the mathematics teaching. I will now show some results of working with the developed model. The students in this task worked together in pairs. Each of them had 1 robot. During the first task, the students was required to familiarize themselves with the robots. The teachers provided a short overview of the different buttons on the robot, and after that the students were asked to figure out what the different buttons were used for, which align with Square 1. The teachers follow up on those activities during the class discussion. It was found important that the students from the start get familiar with the robot, and after that were more prepared to work with mathematics. In this task, the student were asked to deal with the geometric properties of the polygons. Student must let the robot land on all squares, triangles, and so on, and describe the characteristics of each polygon. When students sorted the polygons, it helped them focus on each polygons. This allowed them to increase their knowledge about the geometric characteristics. Students must establish a connection with the robot through CT to create an overview of the polygons on the worksheet and create an algorithm to move the robot from one triangle to another. The students used the robot as a mediating artifact to describe the characteristics of the polygons. Some of the students use gesture to convey the direction in which the robot should turn. The task can be related to Square 4, since the students investigated how to characterize the different polygons from a more student-centered perspective. When students use the robot as a digital artifact, they work with CT to program the robot. Through CT, students try to make the robots move in different order. For example, make the robot move to all triangles. If the robot does not land on the required polygons, the student will consequently debug and correct their code during the task. In this way, students receive CT training when they introduce their work to the class and solve different tasks. Through the use of B-bots, students worked on new forms of geometric representations, and their learning content was represented in a new way, which helped develop students' mathematical, scientific understanding. The teachers worked to create an interaction between spontaneous and mathematical scientific concepts already in the beginning of the class. The students understood the task through this interaction, so they would later perform by mediating the task computational and mathematical intentions. The mediation thus become essential for the teachers to help the students in their development of the mathematical scientific concepts. The teachers was therefore given a central role in the mediation processes as it was significant. The teacher centers activities help to ensure that a link is created between artifacts and mathematical science. If this link is not clear, the students may perceive the use of the artifact as plain without making a mathematical understanding that can be used to solve similar problems in the future. Thanks for listening.